So apparently there's somebody called Faraday who knew something about magnetism, and we're going to change that by one letter tonight and think about magmatism instead, and that's with me. So, how to look inside a volcano. And just as we start, I just want to acknowledge Craig McGee and Kui Liang Sung, whose work is going to form the basis for a lot of what I'm going to talk about today, and then also to the people who provide both data and software to as well, because we, as scientists, can't do things without people and collaborations, and we can't do things without data and the support of companies. So let's get started. If we think about layered rocks, sometimes those rocks can melt. And as shown in this video, those melted rocks, that magma can rise up through those rock layers, through that strata, and intrude those layered strata and feed volcanoes, as shown in here. That magma can solidify and form something called igneous rock, and we get these different types of features in the Earth's subsurface. We have dikes, which are very steep dipping, so they're very vertical. We have things called sills, which are sub-horizontal, so they intrude along those stratigraphic layers. We also have laccoliths. They're like sills, but they have a domal top. You can see they've got a convex up top, and they are lifting up the Earth's surface above them, and that's going to be important for what we're going to talk about later on. We have volcanoes, and then we have the crystallized magma chamber itself, which we call a batholith. So these terms I'm going to use during the talk. So where do we find volcanoes? Well, we find them in areas of melting, and they occur along things called plate boundaries. As shown here, we have areas where a plate is being subducted and there's melting, and we have volcanoes in these arc ranges in through here. We have areas of spreading, like in the North Atlantic, where we're pulling the plates apart and allowing hot material to rise up and extrude at the Earth's surface. We also have hotspots as well, as shown in here, like the Hawaiian chain is related to a hotspot, an area of anomalously hot, deeply buried material which causes extrusions of these volcanoes. If we look at this in map view on the actual globe, we can see again these red triangles in here are these volcanoes. Here's the so-called Pacific Ring of Fire around the edge of the Pacific plate, where it's been subducted below a number of different plate boundaries. And also volcanoes in Iceland, which is where we have the mid-Atlantic rift. So you can see that we have this co-location of plate boundaries and volcanoes and volcanism. Now, what I want to ask you is, do volcanoes matter? And I'm going to show you a video now from Etna, the 16th of March in 2017. If you're squeamish, you might want to look away in a moment. Okay. So you can see in that video, understanding how volcanoes interact with, in this case, ice at the top of Mount Etna, and the damage it caused to the people and the vehicles. Understanding volcanoes is important in terms of human life. We don't just have volcanoes that go bang, we also have these other things called pyroclastic flows, and these are volcanoes which don't necessarily spit out a large amount of lava, but these volcanoes like Unzen here in Japan, we have these pyroclastic flows moving at several hundreds of miles an hour, full of very deadly gases, several hundreds of degrees Celsius, flowing down the sides. This person's doing a fair old Usain Bolt impression in here, with his mates about to run him over. So the story goes, that person actually got into a bunker, and actually the pyroclastic flow went over the top of them, so they were saved. But you can see these very fast moving. So volcanoes are associated with a range of different hazards. It's not just the hot orange lava stuff we need to worry about. So the reason I'm telling you this is because as a scientist, it's nice to have motivation for doing our science. Like, why do we get out of bed in the morning? Like, what do we want to find out, and why is it important? It's important because, like as shown here above Mexico City, the El Popo volcano, there's 9 million people living there, and there's a volcano right on its doorstep. Okay, so can you imagine waking up? I live in Acton. You'd wake up in Acton and look out your window, and you see a great big volcano with stuff coming out the top of it in Shepherd's Bush. And volcanoes erupt regularly as well, so they're hazardous, they're nearby, they erupt regularly. Shown here is a graph going from 1800 through to present day. Here is the number of volcanoes active per year as recorded and observed, either directly or by remote sensing. And these are the large eruptions here. So there's about one large eruption above 0.1 kilometers cubed per year, but there's an increasing number, an average, a long-term average of around 40 volcanoes active per year. So that graph is going up. It's not the prompt for somebody to go and make a Hollywood movie about the fact there's going to be volcanoes increasing through the rest of the time. That actually maps with global population. We're just seeing more volcanoes, and we're observing them more. That's why we're recording more. So how do we study these things? Now we've got that motivation, what tools can we use? Well, we can go and get zero-age lava samples, as shown here on the right, where you go up to the hot lava, this is in Kilauea, and actually sample it and actually look at the chemistry to understand the viscosity, so how runny that lava is and also where it's sourced from. Or on the left here, we can actually do gas sampling, where there's no lava, but there's gases. We can look at sulfur dioxide and carbon dioxide, which are often good signals for magma coming into the bottom of a volcano, and measure those compositions and the fluxes and actually try and understand the volcano's dynamics in that way as well. We can use things called geophysical techniques. So this is where we try and image directly the volcano. So here on the right-hand side, the red is where the seismic waves, so that's the sound waves are traveling very quickly underneath Mount St. Helens in here. So they're where they're going very slowly through Mount St. Helens in here in red, and there's where it's going quickly. And the reason it's going slowly through these areas is because that's where the magma is. Sound waves travel slower through a partially molten mush than they do through crystalline rock. So you can see that image is large scale. It goes down to several kilometers depth, but it's quite smeared. We don't have much detail in terms of what's underneath Mount St. Helens. We can augment or we can add some information to our understanding of Mount St. Helens by looking at these pink circles in here, and these are little earthquakes. So this is little earthquakes where magma's rising, it's causing the rocks to break, and it's sending out seismic energy. And we can see very nicely there's a big train or a big line of earthquakes right underneath Mount St. Helens, and that's because that's where the magma is ascending through up into the main volcanic edifice, the main volcanic cone itself. I just want to kind of then pick on one other kind of technique here, and some of you may remember this volcanic eruption in 2010, the Eyjafjallajökull. I speak Norwegian but not Icelandic. And some of you, I don't know if anybody got trapped anywhere around the world. I got trapped in Chicago, which isn't hardship, and then in Frankfurt, and then in Brussels, and then in Paris. And I made my way back over 10 days. But you remember this closed European airspace. This was a volcano which erupted beneath an ice cap, and the interaction between the melt, the magma, and the ice is what drove that very big explosive eruption like on Etna and caused all that ash to ascend into the atmosphere. So after that, what was studied was how that volcano behaved. And here you can see this is Katla, this is off to the east, and what they had mounted on top of this volcano here were a number of tilt meters. So tilt meters are something you deploy in the volcano, and if the volcano goes up, it will tilt, and if the volcano deflates, it goes down. So you have these stations on the volcano, and they're going up and down and measuring how the volcano is essentially breathing, because magma's coming in, and magma's going out. So we're using these techniques. So now let's look at the record of these three stations going up to that eruption. This is 2009 to 2010, okay? These are displacements in millimeters, so ups and downs. That's on the east flank, the south, and the north flank of the volcano. These are the number of earthquakes, and that's the black in there. The grey is the cumulative number of earthquakes. So what we can see is through time leading up through 2009, these stations were not going up or down, they were just sitting there. Suddenly, the eastern flank of the volcano started to inflate. The southern bit of the volcano started to inflate, and the northern flank of the volcano deflated. So the volcano kind of collapsed on one side and inflated in the other because magma was moving from one side of the volcano to the other. March the 4th, all hell breaks loose. the earthquakes start to nucleate, and there's lots of earthquake behavior, activity, and then there's the big eruption. And look what happens when you have the first flank eruption. Those stabilize. You can see they go back to being flat because you're pouring lava out the top. The volcano just kind of sags back down. And we have kind of a kind of consistent behavior in these two stations. But here we have then a summit eruption, and we see that most of that summit eruption must be fed by lava evacuated from the south. So you can see how we use these different tools to understand how the volcano is behaving. And we end up coming up with a model like this where we're saying, well, you know, Sill 1 and Sill 2, these were the two intrusions associated with that 2010 eruption, 2011 eruption. We can see this is where the eruption site is. So this is basically a guess, right? So we're using those tools, along with some gas work and some other things, to kind of guess what's going on. We can't see this. And what I want to talk to you about today is, like, we can see this in ancient volcanoes. We have some techniques which we can use. Because what we don't want to do is kind of spend our lives making these geophantasmograms, I call them, okay? Because they're very pretty and they get published in Nature and that's all grand, but they're not true, but they're nice, and they're informed by a range of different observational data types, okay? So they are true to a degree, but we can't really see that, or can we? So what if we could image and reconstruct these magmatic systems in 3D and link the ground deformation with what's going on underneath these volcanoes? What happens as well is, rather than kind of giving these geochemists and these petrologists a really hard time, what happens if, as seismic reflection interpreters, we could give them a physical framework within which to understand their gas fluxes or their rock samples? What happens if we could actually build a three-dimensional picture underneath the volcano? And essentially, what if we could X-ray the Earth, okay? That's what I want to do in this talk. So we need high-resolution data, because we need to be able to see the details. We need the data to be big. Volcanoes are bloody huge, right? So we need the data to be really, really big too. We need the data to be cheap to analyze. As academics, I live in Acton in a very small house. So we need the data to be cheap to analyze. You know, we want low computational costs, and we want the data, when it's given to us, to be actually cheap to work with. And, you know, my kind of argument is that seismic reflection data is one of those key tools, and I'm going to take you through what they are. And you know, the stimulation for using this tool I'm going to talk about in the next bit of the talk is based on a principle of uniformitarianism. That is, if we can look at ancient, extinct volcanoes, can we understand modern volcanoes? So if we can look inside old ones, can we understand the ones which are currently active and hazardous? So we're going to have to do this, okay? The complete idiot's guide to reflection seismology in one slide. There's one equation. I'm the least numerate person in the room, I'm sure. So what is reflection seismology? How do rocks relate to these images I'm about to show you? Why can we use this technique? Well, what we have with the seismic reflection survey is we often, with the marine acquisition here, we have a boat, and the boat is sailing along, and behind it, it has streamers, and it has a seismic source. If it's onshore, it'll be dynamite. If it's offshore, it'll be something called an air gun. It releases a huge bubble. And what that does is it creates energy. And that seismic waves radiates out away from me, and it'll reach you all at different times. And it's recorded in these things called hydrophones. Can you see these things trailing behind? And they're reflecting off these different rock layers down in here. They're reflecting back because some of the incident ray in here is transmitted into reflective ray, and some of it kind of keeps going down to the earth, but some of it comes back to these hydrophones. This thing called reflection coefficient in here is controlled by something called the acoustic impedance. What the acoustic impedance simply is controlled by is the density and velocity between the different rock layers. So here I have a sandstone. It's got lots of pore space in it. Seismic energy, because there's holes in this, goes slower through this than through this. Igneous rock, because it's crystalline. So the seismic waves don't get slowed down so much. So if we put this on top of this, or this on top of this, they'll go quickly through here, they'll go slowly through here, and then they'll reflect back off this boundary. So if we look at something called P-wave velocities in here, so these are the speed that these seismic waves go through rock types, don't worry with the details. The sedimentary rocks are slow, 2 to 5 kilometers per second, and the igneous rocks, the crystalline rocks, are fast, 5.5. That is why we can use this technique, is because we get reflections coming back from these crystalline rock types. So already you can see that this technique is sort of built to look at volcanic rocks, because they are so physically different in their density and velocity character to sedimentary rocks. So let's start off simple before I throw you in at the deep end. Let's look at a borehole. So this is a hole that's been drilled into the ground. It's probably about the diameter of this water vessel in here. For scale, these are 10 meters. So this is about 70 meters in here. We have these clastic rocks, sandstones, and then some other clay stones, and then we have an igneous sill, so a crystalline igneous rock in the middle of those sedimentary rocks. If we now look here at the density that's been taken in this borehole from the South China Sea, East China Sea, we can see low densities in the sedimentary rocks, kicks to high densities, kicks back to low densities. And that's because, those crystalline rocks are denser and faster. And we see that as well in the sonic velocities in here. So this is slow rocks. Sound waves go slowly. Sound waves go quick. Sound waves go slowly. So we have the top of the sill and the base of the sill. Okay, so the top and the base of this igneous rock layer. What does that look like? It looks like this. So this is a seismic reflection profile from offshore southern Australia in the Great Australian Bight. The map is in the top right. This is the seabed. Okay, so this is seawater. Now, a lot of the images I'm going to show you are going to be scarily big. I think you're going to forget how big they are. This is 10 kilometers, okay? So this is pretty much from here to Acton, okay? Everything's going to be related to Acton, by the way. And here, the vertical scale in here, this is in something called milliseconds, because we look at things in sonic travel time, but actually, let's just convert that to meter for simplicity. So 400 meters by 10 kilometers, so it's vertically exaggerated, this profile. Hopefully your eye is drawn straight away not only to the seabed, but also these features in here. Can you see these high amplitude features? They're glowing in the data, they're really standing out, and they are these igneous rocks. What we're seeing here are igneous sills and actually volcanoes. Now the amazing thing about this image is the blue horizon here is 42 million years old. It's Eocene, for those of you who know the words, but it's super old. So let's scroll across and have a look. You can see a number of these different igneous sills in here. Look at this giant volcano in here. This is about 0.5 kilometer high, and we can image that fully in 3 dimensions. And we can see that volcano is underlain by that big suite of sills. There's lots of sill bodies underneath. I won't make anybody pass the course by telling me what this is, but that's a laccolith. You remember the laccolith I showed you at the start? Flat bottom, convex up top. And what's really cool about the laccolith, you all notice there's this domes above it. Remember we talked about how the magma being intruded will deform the ground above it. Now, these seismic data, this is an example here from offshore New Zealand, this is another image, it's very densely sampled. Now, how densely sampled is it? So seismic reflection profiles in the modern acquisition, the lines, the X-rays, the sample lines we have are about 12.5 meters apart. That's from here. We'd have a line here, and then we'd have a seismic line probably somewhere over here, okay? So you imagine that, you've got that over an area of, several thousand square kilometers, so they're very expensive to collect. And we get images like this, but because we have such dense sampling, we can make these rather beautiful 3-dimensional images of these sill bodies. So what we've done here is we've mapped every single one of those 12.5 meter space lines with a sill here. Look at the scale bar, that's 1 kilometer. So this sill is about 3 kilometers. That's half the way to Acton. Here, you can see here, we can actually map this sill in here, which is this upper one. So we're just looking at a cross-section through here. And then this lower sill in here, which is this feeder sill. So one way that magma is ascending through the Earth's crust is not by these big magma chambers, but is actually by sills feeding magma to other sills. So we actually have this way of climbing magma up to volcanoes through these sill bodies. So let's have a look at another example from offshore northwest Australia. Again, coloured in red here is one of these sills. Always take note of the scale bar. This is 1 kilometre, so this is a huge thing. This is about 200 metres vertical. So this thing is cut up through almost about 0.5 kilometre of clastic rocks. This is Jurassic rocks in here, so about 155 million year old rocks, looking about 4 kilometers below the seabed here in Australia. And what you notice here is this nice sill, but you also notice, see how the ground is deformed at the red horizon. We can see that the ground has been arched up because we forced that magma in, and it's caused the Earth to go up, just like we saw in the Iceland volcano, where the Earth bulged just before the eruption in 2010. It's a beautiful 2D image, but we can actually make maps like this. So this is the red surface mapped every 12.5 meters. So just imagine this as being like an ordnance survey map for the hikers in the room, okay? Or if you're used to looking at Google Earth maps, this is just colored for height. So this is red is towards you in the room, so high, and purple is low. So you can see that there's a dome. You can see there's a dome, which you can see in the section here. There's a dome in 3D in here. And you can see there's a number of these fractures. You can see there's a number of fractures cutting the top of that dome. So how does that form? I thought I'd show you a kind of rather simple video in here to kind of communicate that to you, because, you know, this technique does allow us to look at ground deformations. What this experiment is showing in here is magma being pumped in here. It's not magma, it's honey. It's being pumped into the crust. It's not the crust, it's clay. And they're pumping it in with a tube. Now, I'm going to run this video, and what you see is they're pumping it in. Can you see the magma? There's the sill propagating. Can you see the ground lifting up above it? So that's just like what happened in 2010. That magma was pumped in, the ground you saw arched up, and there was a number of fractures developed in the top. Now I'm going to show you a video looking on the top of that. Okay, so I gave you a cross-section there. Now we're going to be looking down on this top surface, so this profile, x to x prime, is going through there. So keep an eye now when I run the video again of what's happening there. Can you see that bulge is coming out towards you, and that bulge is fracturing because we're stretching the rocks. We're pushing them up and stretching them, they're fracturing. So that's what we envisage is happening for these folds. And for the nerds in the room, of which there probably are a lot, they're called forced folds, which is quite simple. They're forced folds because they're forced by the magma being driven into the bottom of the volcano in these volcanic terrains. And just to pop back to that laccolith from the Australian bite, we do notice as well when we look at these images, there's something quite interesting about the thickness of these sills and the deformation. We can see these two folds here. These are called anticlines. But if we have a sill down in here, which I'm showing in yellow and pink, it's more deeply buried than this one. It's been intruded deeper than from the free surface. We can see there's a little fold. So what we started to realize from some of this work is depending on where the fold is the sill is intruded into the Earth's crust will dictate how big the uplift is. So if you're trying to use these tilt meters and all these modern techniques around active volcanoes, you've got to think a bit about how much magma is being intruded, but also how deep as well. We can't just assume they're going into the same place and there's the same volume. We can do some quantitative analysis as well, so we can actually measure the thickness, so the distance between the pink and yellow, and look at how thick this is. We can sample across here, and we can also measure how big the dome is, right? So we can do it on a number of different sample lines. And graphs like this, I don't want to put too many graphs or equations in, but this is distance across the sill. So this is 10 kilometer for this laccolith, and this is the fold amplitude and the intrusion thickness in meters. So this is up to 67 meters. The fold amplitude is the black line, it goes down and up. And the intrusion thickness is that one. What you notice, they have the same shape, don't they? Those two graphs have the same shape. So it makes sense that the fold is forming due to the intrusion of the magma. But you notice that the sill thickness, which is shown in here, is greater than the fold amplitude. So we're not having 10 meters of magma in place, and the Earth goes up by 10 meters. We're seeing on average about 30% less uplift of the Earth's surface than there is magma placed into the Earth's crust. So we're not seeing all of the magma if we're recording what the Earth's surface is doing. Just one other graph to capture that. All I want you to concentrate on here is this red line, which is why I've highlighted it. This is the one-to-one line. This is where the thickness of the sill is exactly the same as the amplitude of the fold. And what you notice is with all the data points we have from southern Australia, they all sit significantly below that line. So in a lot of these cases, we're just not measuring all of the ground deformation associated with those cells being in place. And the question is why is that? If we go in the field, so I'm a field geologist as well by design, probably, and passion, but I've been forced to sit in an office with a computer. But if you go to somewhere like Utah and the Henry Mountains, in here you can see, in here there's an igneous sill, and can you notice that there's this orange sandstone layer, and it comes along and it's folded up across the top of that sill, just like the folds we saw in the seismic images. If I show you that maybe in a more simple way, this is the sill in here, 10 meters. It's about 20 meters thick. You can see it kind of thickens this way. What we notice about that sandstone layer is it thins. And that's because as you're forcing magma into the Earth's surface, the rocks above it can do this. They can actually absorb quite a bit of that uplift. So not all the uplift goes up because we actually absorb it. So remember this piece of rock with the pore spaces, this has a porosity of about 20%. We can shorten this by 20% before it does anything, before it deforms. So, you can kind of do this numerically as well. You can measure things like porosity. So we measure the pore spaces in rocks like this. And you notice I've plotted this against this. The porosity is decreasing because of this uplift. So that's one way that the Earth accommodates that. What's even creepier is this image here. This is from the Raton Basin in Colorado, and what's happened here is the igneous sill has been intruded into coal. Not sandstone, not mudstone, but coal. And because coal has lots of organic material in it, lots of water, when you put that several hundred degrees magma in it, what happens to all the water and the gases? Psh, straight out, right? So you actually get in the magma replacing the coal. So here's the igneous sill. These are the coals, and look at the sandstone above. It's not folded at all. It's perfectly pancake flat because the magma has replaced the coal. So we need to bear that in mind when we're thinking about inverting that tilt data from Iceland and similar volcanoes to when we're doing that inversion to understand the materials that the magma's intruded into. And the seismic data has allowed us to kind of collate large amounts of data in our research to kind of test some of those ideas. If we think about some of these kind of volcanic eruptions as well, so these are what we call fissure eruptions. So these are ones which are not necessarily coming out of a large volcano, but in Iceland here, they may come out of a long fracture, okay? So this can be several kilometers long. And you can see in here, you kind of like these lava fountains. In here, we've got lava flows racing away. From here, this is from the 2014 Bardabunga earthquake, which was very closely monitored. So you can see we can have lava being fed by different kind of feeder systems. So not necessarily volcanoes, but these linear features. And what are these linear features? I talked about them on my very first slides. Dikes, damn dikes, okay? And the reason I'm swearing about dikes is because for a seismic imager like me, a geophysicist, these present a problem, don't they? As you can see in this image from Craig from Madeira, you notice that the dikes are vertical. These are the dikes in here. So these are cutting subvertically up, okay? The problem with the technique I want to use is that it's only really good at imaging things which are flat, right? Because all the seismic energy comes down and bounces off. If you have a dike, which is the size of this table, the width of this table, or the width of this room, which is kind of generous, you don't get much energy coming back to your hydrophone, so the imaging becomes very, very problematic. But we know that dikes are a key way in which magma gets from magma chambers up to volcanoes. So how can we use this technique, which I am talking so enthusiastically about, to help us? Here's an image from the southern North Sea. What you notice here are these reds and blacks in here. You're all geophysicists now, right? These are rock layers in the North Sea, so you can see these sedimentary layers. What you notice as well, can everybody see these white zones? These areas where the sedimentary reflections sort of stop. It's a bit odd looking, okay? So that's the base of the Cretaceous, that's the top of the Cretaceous base of the Tertiary there. And if we zoom in to this area in here, can everybody see it a bit more clearly? Can you see that zone in there? And there's a little depression at the top of the Cretaceous. And it doesn't look like much, does it? It's a little, you can see, you come along the Cretaceous, this black, it drops down and goes back up, keeps going. and then there's this pipe underneath. It looks really innocuous, but if you actually make a map, and again, remember, we have these seismic lines every 12.5 meters, so we can actually make a map of that particular surface in there. It's really gorgeous. Okay, so what we've got in here is, this is looking in a map view image in here. Green is low down. Red is kind of slightly higher towards us. And hopefully you can see all of these holes. These are craters. These are craters. You remember in the video I showed you, there was all those lava fountains gushing out in Bardabunga. This is what would have happened on the seabed at the earlier tertiary when these dikes, is what we interpret them to be, came to the Earth's surface and actually created this chain, which is about 40 kilometers long. So these are huge dikes. Has everybody heard of the Great Windsill and the British Palaeoigneous province? If you've been to Arran, yes, there's a few thumbs up from some people from the northeast. These are the same dikes which go all the way from the, like Northwest Islands, all the way through Scotland, all the way through northeast England, and all the way into the southern North Sea. These are several hundreds of kilometers long, and we are starting to image them in these seismic reflection data. So we think that what happened is these dikes came up into a layer which was saturated with water. And remember what happened in Etna, right? And it created a massive crater, and that's what happened here, but, kind of, well, how far long back was that? Several tens of millions of years ago. We can also look at dikes in some of these seismic profiles here from offshore Norway. This is quite cool, but it's quite subtle, but I wanted to keep it in the talk because I think it's like one of the super coolest things I've worked on in the last 5 years. So here you can see, this is offshore Norway, this is the seabed, is just up here. These layers in here, again, just as sedimentary rocks, and you can see how they're all dipping. You can see all they're kind of like dipping that way towards this side of the room. And you can see in here, there's some sedimentary rock layers. Can everybody see these? There's a kind of fabric in the data which is actually cutting at 90 degrees to those sedimentary rock layers, and they are actually igneous dikes as well. And they are Carboniferous age. Well, they're kind of pre-Carboniferous. We think they could be around about 260 million years old. So these are associated with some of the things which we see in the UK as well. But very subtle features in here which we worked on a few years ago. The reason you can see these dikes, remember the previous example, the reason we saw the dikes is because we didn't see the dikes. We saw the craters. The reason we're seeing the dikes here is because if we take that rock layer, which is vertical, and we rotate it, as you can you see how now seismic energy which comes down will reflect back up? So what's helped us here is the fact that the dikes were intruded vertically, but then later tectonism has tilted it, and that's given us just enough interface, just enough of that face to get some energy being returned to the hydrophones. So let's get on to, we've talked now about what I like to refer to, and Craig we refer to as the plumbing system, right, of the volcano. We've talked about sills, we've talked about dikes, we've talked about the ways we get magma up into these volcanic edifices, these cones. Let's go and look at the volcanoes themselves. Like, what can we see inside volcanoes? Volcanoes are huge. They're scary. There's stuff coming out the top of them. They're often in places where you don't want to go on holiday because there's armed groups around them. I went to Nyiragongo a few years ago, and Naimulagira, two volcanoes in the Democratic Republic of Congo, and we didn't want to hang around on the sides of the volcano. Okay, so volcanoes have an issue that they are super important, they can be very hazardous, but they're very difficult to actually image internally, the active ones. But we can go back to places like offshore Australia and actually start to pick apart what's inside ancient volcanoes. So these are the volcanoes I showed you earlier on. These are 42 million years old, so these are these Eocene age volcanoes. There's a little volcano there, that's a couple of 100 meters tall. And then in here, there's one which is about 300 meters tall as well. If you look in detail, can you see these features in here? There's these layers that I'm trying to trace out in here. And in here, these are actually lava flows within the volcano, within that ancient volcano. The reason we think we're seeing the lava flows in this particular example from Australia is because the lava flows, when lava's not coming out of a volcano, sediments are being deposited. right? So we have a lava, we have an eruption, and then we have some sediments, and then we have an eruption. By layering those different rocks with different properties, we actually end up getting reflections inside. And the reason we think the center of the volcano doesn't have those reflections is because where it's densely intruded. That's partly a volcanic magma chamber. We can map out those layers internally. This is a little video. And, as I'm animating on here, you can see we can map out those layers. There's a kind of initial eruption, then we have summit eruptions as well. So we're mapping out different layers and trying to reconstruct the growth of this 42 million year old or 42 to 40 million year old volcano. And you can see here it is building up and has this conical peak in through here. And then we have the final volcano morphology. And that helps us understand things like the way that the lava might change in terms of its viscosity, its stickiness through time, because we can look at the shape changes. And it can also let us know whether volcanoes are going to erupt predominantly from the tops, the summits, or whether they're going to erupt out the flanks. Modern volcanoes, it's very hard to do that, isn't it? Because you have that shape and you don't really know what's inside it. But here we do. And so in this work we did a few years ago, we came up with these conceptual models, which we thought were good, but were actually junk in the end. But we came up and said, okay, volcanoes, as they kind of get wider, they get taller. And so the volcano volume versus the summit height should just track on here. And the problem with science is often, what is it? Data slays a beautiful hypothesis. Is that the term? The data look like that. It's kind of all over the place. Looks like somebody's let off a pellet gun. So this is basal diameter versus summit height. So we went and measured like 80 volcanoes. Well, Craig did because I was paying him. But he measured all these volcanoes. You can see there's this horrible scatter. And we kind of were like, oh, that's not great. But it got published anyway, so it didn't matter. So we ended up kind of like, actually for real, we were kind of thinking maybe the rheology, the viscosity of the lavas were changing through time, therefore the growth wasn't as systematic in these ancient volcanoes. And we know that from modern volcanoes that the composition can change through time. We know that the viscosity can change through time, the gases change, and various other things. Here you can see we had another idea. Okay, maybe these volcanoes don't get any wider, but they just get taller because the lavas get stickier through time, right? So if the lavas get stickier, you have summit eruptions, the lava just piles up on top. It doesn't flow down the flanks onto the side, and that was garbage too. But again, it got published and it returned to ref, so that was good. We can map these things again. This is a nice profile in here. Just hop back to this one. This has this nice suite of sills underneath. So it looks like this was a volcano that was being fed by sills, but we weren't too sure. I've worked a lot with seismic data. This is one of my favorite images of all time. Imagine you're looking at this volcano at present day. The top of the volcano is the black line I'm tracing out. Can you see that? So you'd have a volcano with this beautiful caldera, a beautiful crater at the top, just like a lot of volcanoes that you would draw if I asked you to draw a volcano. But if you look inside, hopefully you can see if I trace down here, this is actually a parasitic. This is a volcano which kind of came out the side of the bigger volcano. So the first volcano actually was like that, where the white line is. And then we've written here parasitic mound base. This is a volcano which actually punctured out the side of this earlier volcano and started to grow through a series of summit eruptions there. So you can see that maybe what we're seeing in modern volcanoes, when we're simply doing remote sensing and looking at maps, we can't get into the guts of the things. We can't really know how they have evolved through time. As you can see in here, some of these volcanoes look like they're fed by sills. This is another beautiful example here. Here's an igneous sill in here, this really high amplitude. This is a basaltic sill, so made from basalt. We have that's the 42 million year old horizon here in green, and there's this lovely little baby volcano right at the tip of that big sill. And we think what happened is the sill was intruded and there was lots of really hot fluids, so what we call hydrothermal fluids. So that's fluid which is transported in the magma and also is expelled from the rocks that are being intruded. And you can see there's a little pipe, and that fed this little volcano with these lovely little lava flows you can see inside the volcano. Not all volcanoes seem to be fed by sills. There's a really nice example here. Sometimes these volcanoes, what we call shield volcanoes, you may have heard the term, shield volcanoes, these very broad, low relief volcanoes. Here's a really nice shield volcano in here. And can you see how it's sitting right at the top of this thing I've drawn in here, which is something we call a normal fault. It's a fracture in the Earth's crust. And when we looked at the Australian data, we saw a lot of examples where the volcanoes, these shield volcanoes, sat at the top of these fractures. So we thought that the fractures were a really important way in which magma ascended. Why is that? If you damage rocks, if you fault and fracture rocks, they become what we call permeable. You can get fluids to flow through them more easily than if the rocks are undamaged. So we see this nice location between the faults and the volcanoes, or at least we did. My career has been a series of thinking something and then it not being true. We then made a map, okay? And this is 10 kilometers. This is like lots of actons through here. And what you notice is the gray, these are the volcanoes. The black dashed outlines are the sills, so they're underneath the map, if you see what I mean. So the grays are your volcanoes. The black dashed lines are sort of showing you where these sills are underneath. And the black lines in here, these are these fractures, these normal faults. And when we actually went and looked at it, we were like, oh, okay, maybe some volcanoes are sitting above these fractures, like here, and here, and here. But then there's all these ones over here, which are maybe being fed by sills, because you can see these volcanoes are all sitting above these black dashed lines, so they maybe are sitting above the sills. And then there were all these buggers in here, which were associated with neither. And we have no idea where they came from, because if you go to the seismic data, there is no evidence that there's sills sitting underneath the volcanoes to feed that magma up, and there are no giant fractures going down to what we call the lower crust, which is a place where we can get large amounts of melting. So we need to kind of get on top of that eventually, I think. But it's a very, like a lot of, if you leave this room with one thing, a lot about what we do scientifically are a bunch of hypotheses we sometimes construct. We then test these ideas, but then sometimes it just doesn't work out. But it does then provide feedstock for another set of hypotheses, or the desire to get more data, or to go and look and try and solve the same problem, but with data from a different location. So just to move on to kind of the final bit of the talk, I've talked about the feeder systems, and we've looked inside the volcanoes themselves. One thing people love about volcanoes are lava flows, right? And I don't know if you remember these spectacular images, and quite devastating images, obviously, for the people living in Kilauea here from Hawaii. So these large lava flows that came out of there and ran across these populated centers. And when you look at these lava flows, you actually see quite a lot of detail in them from above. You can see in here, there's the main lava flow channel here. We can see that there's these lava flow lobes. Can you see these areas in here where the lava has partly crystallized, but it's still setting fire to trees in here. So you can see all these different fabrics on top of the lava flow. You can see the lava flow went here, and then it breached out there, and then it kept going as lava was being expelled from the volcano. One thing we don't often see with lava flows, it's really hard, understandably, because it's really hot. We don't know what's going on underneath them. Okay, so knowing what's going on underneath a lava flow and knowing how thick a lava flow is important if you want to calculate volume, right? So if you want to calculate the volume of lava coming out of a volcano, and therefore something like an eruption rate, right? Because that, for volume, for rate, you'd need volume. It's really hard to do that for obvious reasons. So I'd like to say we thought we'd solve this problem with some data. We actually just stumbled around on some data in the South China Sea and actually found some really nice data which actually imaged inside lava flows. So I want to share that with you now. So this is an image from the top of a volcano or a series of volcanoes in the South China Sea. Just to clue you in, this is high, so you can see these mountainous peaks in here. These are the tops of these volcanoes. These are Miocene aged. So these are about 18 million years old, and these are about 1 kilometer below the seabed, and I'll show you an image in a moment showing that. And, these volcanoes are several kilometers long. So we have a series of these large volcanoes scattered around the basin. So if we take a seismic profile, so let's take one of these X-rays of the Earth. Let's take a line through there. And I'll just step you through this. So this is 0.5 kilometer for scale. So there's the top of the volcano. So the map I showed you is what I'm tracing out there. So hopefully you can all see this volcano, and the seabed is there. And there's the feeders system. So there's a pipe. That's probably a set of dikes. These dikes which we looked at earlier on, which are feeding this volcanic cone. So we said to ourselves, well, let's try and take how best to describe this? With seismic data, we can extract from it how strong the reflections are, right? So we can see how, if you want to make it easy for yourselves, how bright they are. So the really bright reflections or the really dim reflections. So we can extract that information because it relates to the rock types. So what we did is we took a seismic extraction along this horizon I'm tracing out here, this blue, and we had this really beautiful map. So here you can see this is 1.5 kilometers. This profile in here is this one in here. And this is the volcano, where it's dim. And you can see the volcano is dim because there's not many acoustic impedance contrasts because all the rocks are the same. It's just lots of igneous rock inside a volcano. But as soon as the lava flows, you can see the lava flows here, if I trace it out. You see these lovely fabrics, these lovely linear things, just like we saw from Kilauea. So we're actually able to image these lava flows in here, and just a little sketch to orientate you in there. There's a main lava flow channel in through there which splits, which is there, and it splits there and there. There's another lava flow which is what we call sinuous. It sort of snakes away from the volcano. And we can see in here there's these lava flow fans, so this looks just like Kilauea, and then we have this thing we call a lava flow apron where there's lava stuck to the side of volcanoes. We can take seismic profiles through and see these lava flows in cross-section. What was very interesting about this study is, it turns out, and this was a huge surprise, between 70 and 90% of the material erupted from these volcanoes was not within the volcano, it was within the lava flows, which went a long way away from the volcano. So if you calculate the volume of the kind of main lump, if you will, there's lots and lots of material which actually gets transported and flows a long way away, and it was up to 90% on some of the volcanoes. So again, if you're calculating volumes, eruptive rates, and things like this based on satellite imagery of modern eruptive centers, be aware that there is large amounts of material which is outside of there, and the eruption rates and the volumes of the total magma volume or lava volume is much higher. What was also kind of odd, and we stumbled on this as well, is this is a seismic line down a lava flow. So imagine if I take you back. So let's imagine we take a line down the middle of this Kilauea lava flow and try and see what the bottom of it looks like. Because I guess we all think the bottom of the lava flow should be flat, right? Because it just flows out and burns stuff and keeps going and burns stuff, and it should be relatively flat. And then, okay, it could have a little bit of morphology, it could have like a bit of a bump, but actually what's underneath it? What we found when we looked at this lava flow, if you watch what I'm tracing with the green, it's pretty flat, but then you get these ramps. It steps up, and it steps up again. We actually saw that the base of the lava flows here were very, very rugose or irregular. They weren't flat. They actually were cutting down tens of meters into the underlying rock types, and I'll just show you a zoom in here. This is this lava flow in here, 0.5 kilometer for scale. So this profile in here is probably about 6 kilometers, so about 4 miles. This thickness in here, this lava flow was super thick, 100 milliseconds at these velocities, probably about 80 meters. So this is an 80-meter thick lava flow, gone 6 kilometers, and hopefully you can see as well as I trace out here, it goes up this ramp in here as we've drawn in through here. And again, we kind of looked at different ways of playing around with the calculations and saying, well, if we assume the lava flow has a flat bottom, what's the volume? If we assume it's got this very rugose volume, and we were always wrong when we just assumed it had a flat bottom, and it's very important to actually try and understand what the relief is at the base of lava flows. The question here from the South China Sea is, why did this lava flow have such a bumpy bottom? Okay, why did it have such a bumpy bottom? It had a bumpy bottom because the seabed onto which it was erupted, because these are submarine volcanoes, was wet. So you imagine you pour out this 4, 5, 600 degrees more lava onto a wet seabed, and it's heavy, and it's moving, it bulldozes that wet sediment. If you've ever walked out onto a beach or walked into the surf, you just swipe your foot, you can move the sediment out of the way very easily. And the lava is doing something which we call dredging. It's dredging and sinking into that material, and that is why we're getting these huge volumes which are otherwise hidden from view. So just to conclude, on this kind of 50-minute tour of volcanoes, what did we learn from this seismic data? So these data are great. Hopefully I've communicated to you that I think these are one of the most amazing tools we can use, and in our research we use them not just in looking at crustal magmatism, but we use them in a whole range of different things to do with submarine landslides and to look at how salt moves around the Earth and to look for petroleum as well. And these data are all equally as good for looking at these products and the processes of crustal magmatism. What's really neat as well is that we can actually look at the different components. We can look at the plumbing systems, we can look at the sills, we can look at the dikes, we can look at the volcanoes. And from that, using the principle of uniformitarianism, we can try and then understand for modern systems how they behave now and how they may behave in the future, because we have effectively fossilized a volcano. We fossilized a volcano and its plumbing system, and we can image that. I kind of spent some of the talk talking about the ground deformation, and that's really important because one of the key challenges with hazards is warning populations and convincing people that there is a hazard. It's equally as important as communicating that hazard. It's also to put error bars on that, to be honest about what you do and don't know. And sometimes as scientists, we're terrible at that. Sometimes as scientists, we're very good at that, but the authorities are not good at conveying the scientific uncertainty to the populations, and that causes friction and it causes distrust as well. So, here as well, we've shown that we can do some really kind of neat work, we think, about trying to relate the size of these intruded bodies to the size of the ground deformation to try and optimize what we call an inversion of the tilt data. So we have that tilt meter data, the volcano doing all this and this and this, and then we come up with this geophantasmogram. Like, how real is that, and how certain are we? And we also like making friends with people, geochemists, petrologists, people who look at rocks, rock samples, people who look at gases, because we think that this technique is a really good way of making this what we call a physical framework. So you could imagine that we now have a good 3-dimensional to sort of 4-dimensional understanding of what's going on underneath volcanoes and in volcanoes. So then you can understand where your samples are coming from within there and why they may have that different composition or they may have that different types of gases coming out. So it's been a huge pleasure, and thank you that you've kind of spent some time with me tonight. It's great. Thank you.